Hello everyone. In this video I'm going to present again the presentation I gave at the 36th European Photovoltaic Specialist Conference in Marseille. And the title was From the Hot Carrier Solar Cell to the Intermediate Band Solar Cell, passing through the multiple-exciton generation solar cell and then back to the hot carrier solar cell, the dance of the electrochemical potentials. After this long title, what I wanted to do was to review three novel solar cell concepts that are known as the hot carrier solar cell, the multiple-exciton generation solar cell, the intermediate band solar cell, and show how can you pass from one model, from one type of solar cell to the other by making different assumptions about the concept of the electrochemical potential. Before going into details, I would like to review the concept of electrochemical potential in a more familiar context, as it is the framework of the single gap solar cell. Well, in a single gap solar cell, as we know, a photon arrives and creates an electron-hole pair if the material we use is a semiconductor. But the process of absorbing light, I would say, is not the most important one. The important phenomena that takes place is that we are able to do it in a material that it is able to create two different Quasi-Fermi levels. One Quasi-Fermi level linked to the population of electrons in the conduction band, and one Quasi-Fermi level associated to the population of electrons in the valence band. So, and the voltage is actually related to the difference between both Quasi-Fermi levels. So if this is essential, we need to ask ourselves, why is it possible to have two Quasi-Fermi levels in a semiconductor? And for explaining that, we need to remember that in a semiconductor we can have essentially two types of processes. One set of processes, we call them interband processes, and other ones that connect electrons in the conduction band with electrons in the valence band. An example of one of these processes could be the familiar recombination of an electron-hole pair. And another example of process is the intraband processes, by which, for example, an electron loses energy and this energy is released, for example, to a phonon. So the reason why we can have two different Quasi-Fermi levels in a solar cell made of a semiconductor is because we can have interband processes being much more slower than intraband processes. So being these processes slower, what we have is essentially that the electrons are in equilibrium among themselves in the conduction band, and electrons in the valence band are also in equilibrium among themselves. So its population respectively can be described by its own electrochemical potential. But even in this simple context, I will like to call your attention on about two important concepts that we usually give for granted. And the first one is the process called thermalogy, by which an electron loses energy in the conduction band, and that energy is captured by another electron in the valence band. So this process is in fact another process connecting electrons in the conduction band with electrons in the valence band, but it's not a recombination process, a classic recombination process. But since this is a process connecting electrons in both bands, if this process would be fast, it wouldn't be possible to have a split of Quasi-Fermi levels, and therefore it wouldn't be possible to have an output voltage from the cell. Fortunately, this process is not likely in semiconductors, and the reason is that in addition to the energy conservation that is necessary in the process, is also necessary to conserve the crystal momentum, which is represented in this plot by those arrows. And because the curvatures in the conduction band and the valence band are in general different, it is not possible to match those two arrows. It's not possible to preserve the energy of the process and at the same time to preserve the momentum. So that's why this process is unlikely, fortunately, and we don't usually mention about it in general. And another process, we could call it a phonon recombination. And yeah, we are familiar with the process I just mentioned, by which an electron loses energy and this energy goes to another phonon. But typically we describe this process within the same band, but it could eventually be possible that the electron could travel from the conduction band and to the valence band, and this energy could be released to a phonon. But typically we also consider this process unlikely because the energy involved is in the order of 1 electron volt, while the energy available for a single phonon is a few mega electron volts. So in this case, it's not easy through a single process to conserve the energy. So that's why in a perfect crystal, this process is also unlikely. But if it wouldn't, again, it wouldn't be possible to have a split of quasi-electrochemical potentials, and therefore it wouldn't be possible to have voltage different from 0 in a solar cell. Well, yes, another topic which is relevant is that in addition to the absorbers, we need to make electrons circulate through an external circuit, and in order to do that, as Peter Wulfel pointed out in 2009, it is necessary, the essential concept is that we need to create particle selective contacts, which means a material that allows electrons to exit at one end and electrons to enter at the other end, but not the other way around. And those particle energy selective contacts are typically the p-n junctions that we know from in the context of conventional solar cells. Well, after this review, going in particular to the case of the hot carrier solar cell, and discussing again the speed related to the intraband and the interband processes, what we have now is that we consider them equally likely. So there is no one process being faster than the other one. And also we consider that electrons only interact with themselves, so we don't consider electron-phonon interaction. And when we do that, what we have is what we find out is that it is not possible to have only one or two electrochemical potentials, but we are forced to consider one electrochemical potential associated to each energy level, to each electron state. So once we have this picture, we can ask ourselves, then why we call this solar cell hot? And the reason is that you can prove that this description in which the solar cell is cold, but you have plenty of electrochemical potentials, is thermodynamically equivalent to consider the solar cell hot instead of being cold, but characterized by a single electrochemical potential. So a common electrochemical potential for all the electrons. That's why we call the solar cell hot. In this framework, it's worthwhile mentioning that the concept of gap is not important either. Okay, we are used to to think that the gap is important because we associate it to an energy loss, because photons with an energy lower than the gap are lost. But in this case, we could allow for a photon being absorbed within a band, and then in this case, the energy of the photon would be captured and wouldn't be lost. This is different what it happens in the case of a single gap solar cell, because that energy is lost. So in the case of the hot carrier solar cell, we don't care whether we have a gap or not. We have the price to pay is that we have only a single electrochemical potential to describe the full population of electrons. So now if we have one electrochemical potential, we can ask ourselves, then how can we extract a voltage from the solar cell? And the reason why we can extract voltage from the solar cell was given by Peter Wolf, and the idea was that we needed to contact this absorber, the hot carrier absorber, with what they were called energy selective contacts. Those energy selective contacts were characterized by a single energy level. So when an electron transits from the hot absorber to the cold outside wall, it preserves its energy because the energy is a single energy. And while it goes from being hot to be cold, in order to preserve the energy, the electrochemical potential changes from that value, that common value it had at the beginning, to a higher value. And the same happens at the other contact. And it is the difference between those electrochemical potentials what we would measure as output voltage in the solar cell. Well, in the case of the multiple-exciton generation solar cell, well, this cell is typically described in terms of a photon arriving to the absorber. It's a high-energy photon. It creates a high-energy electron hole pair. Then the electron in the conduction band relaxes, but the energy is given. The energy is used to create an additional electron hole pair. Then the electron can lose another step of energy and create another electron hole pair, and so on and so on. So one photon can create, let's say, m electron hole pairs. However, what we find is that if we allow for this process to happen, in fact, what we are considering is that interband processes, this is an interband process, are equally likely than intraband processes because they take place at the same speed. Therefore, in this material, in this description, we wouldn't be allowed to have two electrochemical potentials, but instead one electrochemical potential, because then what you have is like another hot carrier solar cells. These processes I have just described is a subset of processes you can have in a hot carrier solar cell. So you can equivalently, as you did in the case of the hot carrier solar cell, consider that the solar cell is hot, and in order to create a voltage from a single Quasi-Fermi level, as Peter Wolf pointed out, you would need also to contact the multiple-exciton generation solar cell with energy selective contacts. Well, this is what we could call the hot model for the multiple-exciton generation solar cell. It's hot model because the cell is hot. But there is another model in which you can assume the solar cell to be cold, but you need to disconnect the interband processes with the intraband processes. So the way of doing that is that you need to consider that the photon creates at the same time, without any intermediate process, directly m electron hole pairs. the difference is subtle. With the description I made before, because it's not like one electron releasing energy and one step and so on and so on. It takes place. It has to take place in one go. If in this way you can consider electrons in equilibrium among themselves in the conduction band and in the valence band, and therefore you are allowed to have two Quasi-Fermi levels, and in order to create to extract current, you would need conventional particle selective contacts as in the single gap solar cell. In the case of the intermediate band solar cell, what you have is, instead of a semiconductor with one gap, you have a semiconductor with two gaps, and then three bands: the conduction band, the intermediate band, and the valence band. And each band is characterized by its own electrochemical potential. This is the classical description of the operation of the intermediate band solar cell. But now you could take the concept further and assume that you have a material with three gaps and then four Quasi-Fermi levels, and so on, so on, so on. So you take the number of gaps to infinity. In fact, you arrive to a model in which you have a lot of bands that you could describe as a continuum of energy levels, and each one described by its own Quasi-Fermi level. So this is again the hot carrier solar cell model. So in the limit, you would be forced to describe the operation of the intermediate band solar cell as a hot solar cell with a single Quasi-Fermi level, and you would need to extract energy selective contacts, to place energy selective contacts in order to create an output voltage from the solar cell. Well, thank you very much to our sponsors, the GRECO project funded by the European Commission, the project 2 Gaps funded by the Spanish Ministry of Science and Innovation, and the project Madrid PP2 funded by the European Commission.